Let's move on to the next subtopic, that is called derived physical quantities. What is derived physical quantities? Derived physical quantities is that is combination of two or more basic physical quantities. For example, you can take area, the unit should be simple m square. Considering volume, the unit should be n cube, simple m cube. Considering velocity, the unit should be ms minus 1. Considering acceleration, the unit should be ms minus 2, and followed by force, power, momentum, pressure. They all got the different unit. Those are called derived physical quantities. Derived physical quantities. Let's move on to the derived physical quantity, and we can find the unit and the dimension of those derived physical quantities. Let's move on to the first example. The first one is area. We are going to find the unit and the dimension of the area. What is area? Area, that is length into breadth. So what happens? The unit should be simple m into simple m. Then what happens? That becomes m square. M square. When finding the dimension of area, you have to make use square brackets, right? Square brackets in order to find the dimension of area. In order to get the dimension of area, you have to take the dimension of length and breadth. Length and breadth. So that is capital L into L. Therefore, the dimension of area becomes L square. L square. Okay. Then the next one is, the next physical quantity is volume. Volume, that is length into breadth into height. So we can follow the same procedure in order to get the unit of length, breadth and height. So the final conclusion is volume got the unit as m cube, simple m cube. And let's move on to the dimension as well. When considering or when finding the dimension of volume, you have to consider the dimension of L, dimension of length, dimension of breadth and followed by height. So therefore it becomes L cube. Let's move on to the another physical quantity, that is velocity. What is velocity? That is rate of change of displacement. According to the definition, how would you get the unit of velocity? So the equation should be displacement divided by time taken. Displacement divided by time taken. When considering displacement that belongs to length, therefore the unit should be simple m meters. When considering time taken, we know that the unit of the time taken should be simple s. When simple s goes up, that becomes ms minus 1. That becomes ms minus 1. When considering dimension, what happens? You know the dimension of displacement, that is capital L, then divide by the dimension of time taken, that is capital T. Therefore what happens when capital T goes up, it becomes LT minus 1. So our conclusion is velocity got the dimension as LT minus 1. And make sure using capital letters when you are providing the dimension of given physical quantity. Right. The next physical quantity should be acceleration. Acceleration. What is acceleration? Acceleration, that is rate of change of velocity. So in order to find acceleration, what you have to do is take the ratio between velocity change or velocity difference divided by the time taken. So the ratio between velocity change and the time taken gives you the acceleration. The unit of the velocity should be ms minus 1 divided by simple as the same procedure we can follow. So when s goes up, that becomes negative. Finally, the dimension, the unit of the acceleration becomes ms minus 2. ms minus 2. Right. Then finding the dimension of acceleration, what we have to do? In order to get the dimension of acceleration, same procedure we have to follow what we did in previous cases. So then you have to get the dimension of velocity change, same as velocity. Therefore it becomes LT minus 1. Then you have to consider the dimension of time taken as well, that becomes capital T. Then what happens? It goes up. Finally, the dimension of the acceleration becomes LT minus 2. The next physical quantity, that is very important physical quantity under physics, that is none other than force. Force. What is the equation for the force? So the well-known equation is F equals ma. What's that? That is F equals ma. So force equals mass into acceleration. Mass into acceleration. Then we know the unit of the mass as simple k simple g, and followed by acceleration, that is ms minus 2, as we calculated in previous. So the unit of the force becomes ms minus 2. You can consider the newtons as the unit of force, accepting kg ms minus 2. Let's move on to the dimension of the force. How would you take the dimension of force? We can follow the same procedure. In order to get the dimension of force, dimension of mass is capital M, then dimension of acceleration, that is LT minus 2. Therefore, it becomes MLT minus 2. That is. Let's move on to the momentum as well. What is momentum? Momentum, very familiar physical quantity under physics. So you can take mass into velocity or force into time taken. Mass into velocity. The unit of the mass is, as we know, kg, simple k simple g, then ms minus 1. Therefore, unit of momentum becomes kg ms minus 1. Then finding the dimension of the momentum, the dimension of the mass is capital M, then LT minus 1, it becomes MLT minus 1. MLT minus 1. Right. Then what would be the next? Let's move on to the work done. what is work done? How would you get the work done? That is force into displacement. Therefore, you can consider the unit of the force as kg ms minus 2 into just another simple m. Therefore, it becomes kg simple m square s minus 2. That is the unit of work done. Instead of this kg ms square s minus 2, you can use capital J as well. That is called joules. Then the next physical quantity which is related with the work done, that is power. Power equals work done divided by time taken. Work done divided by time taken. So when considering the unit of the work done, you can take that as kg simple m square simple s minus 2 divided by s. This simple s goes up. Finally, it becomes kg m square s minus 3. That is power. Now we can consider the next physical quantity as charge. What is charge? Charge gives you current into time. Current into time gives you charge. So when considering current, the unit should be capital A, that is amperes, into simple s, that is AS, ampere second. Instead of ampere seconds, you can use capital C. What does mean by capital C? That is Coulomb. Let's move on to the next physical quantity, that is voltage difference. Voltage difference. So in order to find voltage difference, what should be the equation? In order to get the unit of the voltage difference, you have to consider work done divided by charge. Work done divided by charge. When considering work done, the unit should be, as we got kg m square s minus 2 divided by the unit of charge. What is unit of charge? As we got in the previous case, that is none other than AS. What happens when AS goes up, both getting negative powers? So kg m square s minus 3, then followed by a minus 1. That is voltage difference. Voltage difference. Then we can find resistance. How would you find resistance? Resistance. What is the equation for resistance? That is under current electricity. The well-known equation is V equals IR. When R subjecting, that is voltage difference divided by current. Voltage difference divided by current. Then what we have to do? In order to find the unit of the voltage difference, as we got, we can use kg m square s minus 3 a minus 1. Then it should be divided by capital A. Then what is our conclusion? When A goes up, that is kg m square s minus 3 a minus 2. We can find the dimension of these physical quantities. What are those dimension? Under resistance, it should be the voltage difference. It should be m L square t minus 3 I minus 1 divided by capital I. Therefore, final dimension should be m L square t minus 3 I minus 2. That is the dimension of resistance. When finding the dimension of the voltage, same procedure we can follow. That is ml square t minus 3 I minus 1. Considering power, it should be ml square t minus 3. Considering charge, it should be IT, because the dimension of the current is capital I and the dimension of capital T is just T. Right. Then we can go through capacitance. Capacitance, which is under electrostatic. When finding the unit and the dimension of capacitance, you have to make use the equation like Q equals CV. Q equals CV. Q is charge, then C is capacitance, V is voltage difference. In order to find the unit of the capacitance, charge divide by voltage difference. Charge should be divided by voltage difference. When considering charge, the unit should be AS as we got. When considering the unit of the voltage, it should be kg m square s minus 3 a minus 1. When these physical quantities go up, minus 1 goes up, it becomes plus 1, then altogether a square, then s to the power 4, m to the minus 2, then kg minus 1. Using these units, we can get the dimension of capacitance. We can follow this procedure in order to get the dimension of given physical quantity. So you have to convert these 4 units into dimension with their own powers. For example, when considering capital A, the capital A is the unit of current electricity. Okay, so then the dimension should be I, and make sure to put square as well. Then considering simple S, t to the power 4, considering simple m, L to the power minus 2, L minus 2, then considering kg, m minus 1. No need to follow a particular order. This should be the way of getting dimension using the derived unit. After capacitance, we can go through the other physical quantity such as magnetic flux density. Magnetic flux density. The equation is F equals BIL. What is F? F is force exerting on the current carrying wire. Capital B, what we are looking for, that is magnetic flux density, and capital I is current, and length is the effective length in between two rails. In between two rails. Now let's go through magnetic flux density. Magnetic flux density, as I mentioned earlier, the equation should be force divided by current into length. The unit of the force, what is the unit of the force? As we got in the previous case, it should be kg ms minus 2. Kg ms minus 2 divided by the unit of the current is amperes and simple m, then mm getting cancelled off, so kg a minus 1 s minus 2, and we can convert the unit into the dimension directly. We can convert that unit into dimension such as m I minus 1 t minus 2. That is the magnetic unit and the dimension of magnetic flux density. Let's move on to another physical quantity under magnetic field that is very related to the there's a close relationship between magnetic flux density and the next physical quantity, that is magnetic flux. Magnetic flux. When finding the magnetic flux, what you have to do is, there is a well-known equation such as pi equals B into A. That is magnetic flux equals magnetic flux density into area. So what is the unit of magnetic flux density? As we got the previous case, it should be kg, then what? Kg a minus 1 s minus 2 into m square. Finally it becomes kg m square a minus 1 s minus 2. You can convert these units into dimension directly, that is ml square I minus 1 t minus 2. That is the unit and the dimension of magnetic flux. Now we can move on to the pressure. What is pressure? That is called force per unit area. In order to take the unit of the pressure, force should be divided by area. Force should be divided by area. What is the unit of force? As we know, that is kg ms minus 2 divided by m square. So m getting cancelled off. As a result of that, the remaining m goes off. Kg m minus 1 s minus 2 is the unit of the pressure, and the dimension should be ml minus 1 t minus 2. That is pressure. Now we can go through stress. What is stress? That is very close relationship between the stress and pressure. So stress is force divided by area. Okay, that can be taken as tensile force divided by area. So all in all, the unit of the stress should have the same as pressure. The unit of the force is kgms minus 2 divided by m square. Finally it becomes kgm minus 1 s minus 2 as we got under pressure. Right. Then we can go through the strain. Strain, that is extension divided by the initial length. Extension divided by initial length. What is extension? That is difference between final length and initial length. So in order to get the extension, take the gap between those physical quantities as I mentioned earlier. Therefore the unit becomes simple m, and the initial length, as we know, it is kind of a length. Therefore the strain becomes unitless or dimensionless. What is the next physical quantity? We can go through Young modulus. So in order to find Young modulus, take the ratio between stress and strain. Stress divided by strain gives you Young modulus. So as we calculated, the unit of the stress should be kg m minus 1 s minus 2, but the strain doesn't have any unit or dimension. Therefore the unit of the Young modulus becomes kg m s minus 1. You can convert the unit into the dimension as we followed in the previous case. Therefore it becomes ml minus 1 t minus 2. ml minus 1 t minus 2. Then what would be the next physical quantity? We can consider mass per unit length. What is mass per unit length? When defining pressure, pressure is force per unit area. Therefore, we have to take the ratio between force and area. So, in order to take mass per unit length, you have to consider the ratio between mass and length. Mass and length. What is the unit of mass? That is simple kg, and length simple m. So finally the unit of the mass per unit length should be kg m minus 1, and the dimension should be ml minus 1.